All right, so this is notes E on titration curves and indicators, part 5 of the notes. So titration gets a little bit more complicated in IB. Yes, we've covered titration already in Unit 1B. So some of this beginning part is going to sound very familiar, but I want to kind of make sure we have a solid foundation and it's fresh on your brain. So usually the idea is to determine how much acid or base is in the solution. We call that standardizing the solution. We're basically trying to determine the concentration, right? The amount of particles that are in the substance. So typically there's an unknown that's, for example, an acid, and then you would titrate with the known concentration of base or vice versa. So you have to know the concentration of the thing that you're titrating with. So you know one of the two concentrations, and you're trying to determine the other. And then we'll measure each volume. The idea is to add exactly enough that it is, neither one is limiting, like the mole to mole is equal, very similar to what we did in the mole ratio lab. Imagine where we were reaching that peak and neither one was limiting. The equivalence point is where the acid and base comes together, and neither one is more dominant, hydrogen or hydroxide, in the solution. So the idea is that we're reaching that equivalence point where the mole of acid is equal to the mole of base. And of course, IB has a special name for it that you'll see sometimes, the stoichiometric point, which I get where that comes from because the moles are equal. All right, so then what we're going to get into a lot more in IB is the titration curve itself. And when you do the titration lab, you're actually going to graph your own curve using a pH meter during the titration. So on a titration curve, the titrant is always what you put on the bottom. So we're going to measure out how much, for example, acetic acid goes into the Erlenmeyer flask. And then in the burette, the titrant is the sodium hydroxide here. So it would be the sodium hydroxide that goes on the bottom, because the concentration of the acid is not changing during the titration. It's the concentration or the amount of the base that you're putting in that's changing. So that is your independent variable. And then what you're going to measure in response to is the pH of the solution that's we're adding it to, the pH in the Erlenmeyer flask. So your pH meter will go in the flask and you'll drop the base inside. So there are 4 main points, and we're going to need to do independent calculation depending on which of these points we're at. The calculations are very different for each step. It's important to understand not only the calculations we're going to walk through, but also theoretically what exists in the flask at each of these points. The first point is the starting point. At this point, 0 base has been dropped into the flask. So at that point, you have only the analyte or this acetic acid. Then you have another point, and it doesn't necessarily have to be exactly right here. It could be anywhere here. We'll talk about like maybe strategic choices for what point to use. But any point before the equivalence point would be your second point. Your third point needs to be the exact equivalence point, and then your fourth point will be sometime after that. And the fourth point is once we have excess base. So the idea with the fourth point is that you're treating it mostly at looking at what base is present there. It's going to consume all the acid and then you'll have extra base. So 2 is kind of the most complicated point because there's different reasons why you might pick it. For example, halfway to the equivalence point, or at different times, it might ask you to solve for different times before. And that's a little tricky because you have to use stoichiometry to figure out how much exists at that moment based on how much base is given. 4 is the easiest because it's just excess base. So we don't even have to do an icebox on that one. So far, so good. 4 main points. We're going to go into a lot of detail on each one in a minute too. All right, next big surprise. IB has weird units for this section. Instead of using molarity, which is typically known as moles per liter, we're going to use millimoles per milliliter. And of course, if they're both milli, then it's really the same. So when they give you molarity, you can treat it as millimoles per milliliter. And it actually does make the math easier. It's not an annoying unit this time. I will say that it is easier because you're going to be given volumes in milliliters, not liters, right? When are we adding like liters and liters of solution to something? So by treating it as milliliters, it would be millimole for it to still be the molarity is equal to that. So you're going to see molarity in millimoles per milliliters is pretty much used interchangeably. It'll give you usually molarity in the question, and then everything will be worked in millimoles. All right. So don't let that throw you off. It actually does make it easier. All right, so there are three main types of titrations. The first type of titration we did in honors, and we did back in Unit 1B. Strong acid, strong base, complete dissociation. And the only reason why we didn't do weak acid or weak base is because we didn't know about icebox then. So we kept it to strong acids and strong bases, where there's no equilibrium present. With weak acids or weak bases, we need to use iceboxes to figure out their concentrations at equilibrium. You would always titrate a weak acid with a strong base or a weak base with a strong acid. You would never titrate weak with weak because the curve is completely unpredictable. So let's take a look at some details here. Strong acid and strong base. Very straightforward. Just do the stoichiometry. You can use the normality shortcut if they're not asking for, like, remember in Unit 1B, they would ask for moles along the way. It was like a 3-step question. So if they're not asking for that, then you can use the normality shortcut because there is no equilibrium. It's just complete dissociation. On the flip side, if one of them is weak acid with strong base or weak base with strong acid, there is going to be an equilibrium. So the stoichiometry is how we're going to figure out the initial concentrations. And then the do equilibrium means do the icebox calculation then. So we're going to account for that equilibrium concentration. Stoichiometry used to get initial, and then equilibrium to be able to use with decays. All right, so let's look at some examples of the main titration curves so that we can see the different pHs that we're looking for. And this is going to tie in with indicators later. So the indicator, by the way, always goes with in the Erlenmeyer flask so that you can see as you're adding the titrant when the color is changing. And we will use an indicator more as a qualitative support of your analysis in the titration lab. We're going to go to the next slide. Oh, okay. Did I go too far? Okay. So the pH of the equivalence point actually does change a little bit depending on what salt is formed from the titration. So think back to the hydrolysis lab. Sometimes we put the salt in and it made an acidic solution. Sometimes we put it in and it made basic solution. Sometimes we put it in and it made a neutral solution. We're mostly going to be focusing on the new stuff with the weak acids and bases. So typically you'll see it forming either an acidic or basic solution. Remember, it only formed neutral solution if they were both strong. So in this example, we are titrating with the sodium hydroxide, a strong base. And so this black line here would be what would happen if I have the strong base. Why is it not? There we go. I'm sorry. So we're titrating with the base. So if the acid was strong, if this was strong acid with strong base, then the black line would form. But if you take a weak acid and titrate it with the strong base, you're going to get more buffering because of the conjugate that's formed. So basically, strong means steep, whereas if it's weaker, it's going to be like less steep. It's going to be buffered more because the weak acid will form the strong conjugate base. And then on the flip side, since we're titrating with hydrochloric acid, if I have the weak base, then it would be less steep than the strong base. The order of these animations are throwing me off. There we go. Can you guys see that better? Okay, so that's the main idea between these last two slides, is that we want to make sure that if it's strong versus strong, it's nice and steep, and then the weaker it is, the less sloped steep. All right, so now there's 4 main types of titration curve shapes, and you should be able to identify them by their shape. If it curves up, like starts low and curves up, then it started at a low pH. So it would be starting with an acid and we're titrating with the base. This other direction, we're starting up high with the high pH. So we'd be starting with the base and then we're titrating with acid. So first of all, by the direction of the slope, you should be able to figure out. And what I usually look for is whether the pH is high or low to start with. And so then you know that you're starting with that acid or base. and then the titrant is always on the x-axis too. So put 2 and 2 together there. If they're both strong, so next point, talking point here, if they're both strong acid with strong base, then the equivalence point will be the exact neutral pH of 7. And so that equivalence point you'll see at 7. If one of them is weak, it's going to shift that equivalence point. So for example, if you had a weak acid, then you're going to get different buffering. And so the pH at the equivalence point, we can see here, the equivalence point is going to be more in the basic range because it's the strong base. The buffered solution would be basic. So we're closer to like 8 here at the equivalence point. I'm not saying it's going to shift the equivalence point up to like 14, but it's going to shift it so that it's higher than 7. And then on the flip side, if you have the strong acid with the weak base makes the strong conjugate acid. All this is pushing the solution to be in the acidic range. So we've got the pH, which would be less than 7. The equivalence point here looks like it's about 5. So lower than 7 typically. So based on the pH at the equivalence point, you should be able to predict what type of titration is occurring. If it's at 7, it is a strong acid, strong base. If it's in the acidic range, it's the strong acid with the weak base. And if it's in the basic range, then it's the strong base with the weak acid. Strongly. Really because of the conjugate, but we've talked about that already. All right, so just so you can kind of see it once, not that we're going to be able to use it at all, this is an example of a titration curve with 2 weak things. So this is acetic acid with this ammonium hydroxide, weak paired with weak. The graph is basically unpredictable, so we're never going to use this to titrate. If you have a weak acid, you have to titrate it with a strong base and vice versa. This pH happens to be around 7. That may or may not be true. The shape of the graph can get kind of funny. Don't titrate with weak stuff. Whatever's in the burette should be strong. All right. So let's wrap back around to the idea that if we have a weak acid, then it's going to create this buffer and it's going to change the shape of the graph. Here's an example of continually decreasing the concentration. The strongest acid, an actual strong acid, is this red curve. And then remember that Ka is proportional to the strength. So the bigger Ka means a stronger acid. And that goes back to the fact that K comes from product over reactant. And so more product would be more dissociation. So that's going to lead to that higher K value. So if we have a higher K, keep in mind how the negative exponent works. 10 to the negative 2 is bigger than 10 to the negative 10, right? More decimal places out. So the larger numbers are down lower. And then as you're going up towards the purple line, that would be our weakest acid with the smallest K value. So we're getting more and more buffering as we go with weaker and weaker acids because of the type of salt that's formed. So let's think through, there's like 3 points that I want to make on this graph. So first of all, notice on the y-axis, they're not all starting at the same point. Right? You kind of think, well, if it's the same concentration, shouldn't it start at the same point? But only strong acids completely dissociate. So that's going to have the highest concentration of hydrogen ions in solution, aka the lowest pH. And then the weaker the acid, the less dissociated hydrogen ions, and so the higher the pH. Weak acids dissociate less hydrogen ions in solution means that it is less acidic or more basic. And so that's going to creep up higher and higher on the pH scale. Make sense? So different starting points there. The weaker the acid, the more rapidly the pH rises in the early part of the titration, but then it slows down as you near the equivalence point. So you see kind of the steeper part, this purple curve has this big jump at first, whereas the stronger acids are more kind of just plateaued at first. And then we get the steeper jumps on the stronger acids close to the equivalence point and more mild jumps towards the equivalence point with the weaker acids. You see on the graph where I'm talking about there, steep jump on either side. And that is because of how the buffer works. So I'm using the example that we used a lot in the last part of notes. picture acetic acid, weak acid reacting with sodium hydroxide, strong base. That's going to form sodium acetate and water. So the sodium acetate contains the acetate, which is the conjugate base of the weak acid. And what do you need in solution for a buffer? The weak acid and the conjugate base, or salt of the conjugate base. So the fact that both of these things are in the solution create the buffer, right? And so the more of these things in solution, the more it buffers. All right, and then the third point is that the pH at the equivalence point is not 7. So we looked before at how that can shift up or down depending on whether it's weak. So in this case, it's weak acid, so it's going to be shifting in the acidic range. And the weaker the acid, the higher the pH at the equivalence point, because again, you have less dissociation. All right, all good on our first page. All right, so now let's really highlight those 4 points that I touched on. Oops, sorry, fun fact. This is not something we're going to actually practice. Everything we're going to do in IB will be monoproduct, meaning having one hydrogen attached to whatever the anion is. But just something that I wanted to show you, or I'm supposed to show you, just so you aren't like completely confused when you see it in the future. Each hydrogen dissociation would have an equivalence point. So if I have something that's diprotic, like carbonic acid or sulfuric acid, when it first loses a hydrogen to form bicarbonate or bisulfate, you're going to get a little jump, and then it'll plateau again. And then once it loses the second hydrogen to form just regular carbonate or sulfate, you have a second equivalence point. So just like the different steps would work in a mechanism and activation energy, same thing with the pH curves. Okay, now let's look at the 4 main steps that we're going to need to use when we calculate the titration curves, figure out the pH on the titration curves. So the first point is actually the starting point. And at this point, there has been no titrant added. So if we're starting with acetic acid in the Erlenmeyer flask, then we're going to handle this as if only acetic acid is in the flask. So basically, it's just that acid, weak acid reacting with water to form its conjugates, just like we've done in previous icebox problems. The second point, and this is the one that can get a little tricky of where to choose. Go back a little bit, yeah. The first point was the starting point, no titrant added. So if you're got the acid in the flask, the titrant would be the base, or vice versa. There's no titrant added, so it's just the pure weak acid or base that's in the Erlenmeyer flask. You're unknown. You're unknown. Okay. So then the next part, this next step, we just basically want to pick something that's before the equivalence point. So obviously not the starting point, something with a little bit of titrant added to it, but not anything past or equal to the actual equivalence point. So some point in here. Remember that if you have a weak acid or base, halfway to the equivalence point, you have the buffer. The equivalence point itself is where the mole of acid equals the mole of base. And the whole pH equals pKa thing, we figured out that if we have twice as much of the weak thing compared to the strong thing, then we have the perfect buffer, right, where pH equals pKa. So if we have pH equal to pKa, aka at half the equivalence point, that can be really useful. And that's something that I would remember when you do the lab. Make a little note to yourself. This is a lab strategy. It makes the calculations a lot easier. It allows the graph to do some of the solving for you. All right, so at this point, regardless of where you pick, whether you intentionally pick halfway to the equivalence point, or we're actually going to be given a specific volume in our calculation that we have to solve for, you're going to have to use stoichiometry in order to figure out what the initial concentrations are, because only some of the neutralization will have occurred. Not exactly half, not all, not none, an exact amount. So because of that, we're going to have to do stoichiometry to figure out how much is neutralized, and then we'll use those for initial concentrations in an icebox. So first, stoichiometry allows the acid or base to react The strong one will be your limiting reactant. Strong limiting reactant. And then that's going to react with the weak. And so you're going to figure out what the solutions, how much is formed when they form the conjugates. Then you're going to actually do the equilibrium. So that means do your icebox. It says or Henderson-Hasselbalch equation here. HH means Henderson-Hasselbalch. And there's one part when we do our calculation where that's going to help us out as well. It's another way to handle concentration. I know the mechanism of the calculation might seem a little vague right now, but basically the takeaway that you should know before we get into the calculation is we need to determine initial through Stoke and then determine or then use ice to get the pH. Another minute. Good. I guess this is almost a touch. All right, so the third point is actually the hardest one and the longest calculation. This is why I made the note takers a little longer, or a little more space here. At this point, the mole of the acid is exactly equal to the mole of the base. So the IB book uses molarity of acid, volume of acid equals molarity of base, volume of base. This is exactly what I told you not to do in honors. M1V1 equals M2V2, because it doesn't account for the stoichiometry, the balanced equations. You had to use NAVA equals NBVB, normalities, where the, if you remember normality, you just take the molarity and you multiply it by the positive oxidation numbers. So for example, if it was like barium hydroxide, barium has a +2 charge, and so you would just double your molarity. So in an acid case, because they're avoiding diprotic acids, they're not giving you diprotic pH curves or anything. They're using M instead of N, which does work because it's monoprotic. But I want you to know that for the future, if you have something that's diprotic and you don't use normality, you don't double that molarity, then you're not going to get the right answer. It's only because it's monoprotic that you're using M. But that's the formula that's like in the IB book, so I didn't want to like change it on you. Just know that it's because it's monoprotic. Okay, so now the fact that these things are equal is what's going to drive the calculations on that part. I thought I got rid of all those clicky noises. Obviously, I missed one. Anyway, the last point is beyond the equivalence point, so way past it. And typically you want to go pretty far up in that plateau because the calculation assumes that all of the acid is consumed and this is just now excess base. So it's like past the neutralization. Excess titrate. So we would be basing our calculation just on how much NaOH is left. All right, next we're going to get into a big old giant calculation. Any questions before we do that? Okay, so this is the question, and I'm going to just switch over to the dot chem a second and work this out a little bit more by hand, just so you can see where we're at in the notes. Titration of strong base with weak acid. It's asking us to calculate the pH at different points. It gives the concentration of potassium hydroxide. It gives the concentration and volume of the benzoic acid. So this must be what's in the flask. We're trying to figure out our pH curve. We have the Ka given, and we're being asked to find the pH for 3 different volumes. I'm going to go ahead and work this with the idea that I actually want to find the pH of 4 different things, those 4 different points that we went over, because a very similar question might ask you to predict your pH curve. And if you calculate the pH at those 4 different points, you can make the curve. So rather than just doing these 3, I'm also going to do it at 0 milliliters, 20, 25, and 30. And that'll be those 4 different points. All right. Dot chem, here we go. In just a second to switch it up. Sorry, I know it takes a minute. All right, there we go. So this is basically what we have so far that we've been given. The concentration of the potassium hydroxide, which is going to be our titrant. That, by the way, is equal to the concentration of OH. So when we do some of the icebox calculations, they will just say OH, but because it would dissociate 1-to-1, those concentrations are equal. Don't let that throw you off. And then they gave it to us as molarity. So remember we talked about the IB units of millimole per milliliter. So it's going to be much more helpful to work the problem in these units. That's the plan. All right, then we were given the concentration of what they said was benzoic acid, and in the word problem, they gave it to us as HC7H5OH. That format is our acid format, where the hydrogen is in front, and then it's referring to what would be the conjugate base of the benzoic acid after that H removed, second. So remember, benzoic acid has benzene with the extra carbon and then OOH. So they also write it, even throughout the same problem, they kind of switch back and forth between these two ways. So C6H5 would refer to the ring, and then COOH is the carboxylic acid group. The conjugate base of which would be just removing this hydrogen, removing the hydrogen here of the carboxylic acid, proton donor. And so it would be written out, they write it out like this with the, again, benzene ring and then the COO minus. First time I went through this, I kept saying like, where's the other C? It's 7, it's 6. It's just because they're writing it organically. All good there, orgo-wise? Okay. The other information they gave us about the acid was that there was 50 milliliters of it, and that the Ka was 6.5 times 10 to the negative 6. This is the given information that I'm going to refer back to. Before you can even start, you have to find the equivalence point. So at the equivalence point, we know that the mole of acid should be equal to the mole of the base. Because it's monoprotic, I am now going to use molarity of acid, volume of acid, equals molarity of base, volume of base. So the molarities I'm going to pull from are the 0.05 and the 0.025, and then we have the volume of the benzoic acid. So the molarity of the acid was the 0.025, and the volume was the 50 milliliters. Then the molarity of the base was the 0.05. And we are trying to find the volume of base. So I'm going to do 0.025 times 50. And then divide by 0.05. And so it's 25. So the volume of base equals 25 milliliters at the equivalence point. And by the way, on the PowerPoint, they keep using EQ as an abbreviation, but I kept confusing that with equilibrium, so I'm using EQV. So what that helps me with is they have told us that we want to find it at 20 milliliters, at 25 milliliters, and at 30 milliliters. And I mentioned I also want to do at 0 because it'll give us our 4 points. And that's because 25 is the equivalence point. So 0 would be the starting point, 20 would be before, and 30 would be after. And if you have the pH of these 4 points, you can plot your titration curve. You can just trace through. All right, so far so good, ready to dig in? So our first calculation I want to do is the first starting point. at this point, we have only acid. First point is our starting point, where you literally only have the benzoic acid in solution. So at this point, I have the benzene ring carboxylic acid group. The hydrogen will dissociate to form the hydrogen ion, and then this would be the conjugate base of the benzoic acid. All right, so we know what the concentration was to start with of the benzoic acid, and that was the 0.025. And then we know the product concentrations are 0. We know it's a 1-to-1 change, where we're using reactant making product. So if I were to write this in terms of x, it would be 0.025 minus x. That's next. But Ka is small. So I'm going to assume that x is way smaller than the initial concentration to get rid of this guy. And you don't have to check the 5% rule, you just write that you're assuming it. And then since I have the Ka, I can now plug into the Ka expression. So Ka is product, H plus, and conjugate base over the weak acid. That's our equilibrium expression. Product over reactant, coefficients are 1. So I'll plug in the Ka on the left, 6.5 times 10 to the negative 5th. And then on top, I have my products, which are both x. And on the bottom, I'm just going to use 0.025. And now I can solve for x. Okay. So 6.5 e negative 5 times 0.025. That'll get rid of these guys, but it's still squared, so I need to square root. All right, so it's going to be 1.3 times 10 to the negative 3rd. And we have that equal to our concentration here of hydrogen. So that is my H plus concentration. One last step, what we need to do is find the pH every time, right? So that's just simply pH equals negative log of the hydrogen concentration here. Negative log, oh, I shouldn't have cleared it, 1e, negative log 1.3 e negative 3. So the pH, 2 sig figs, so 2 decimal places, is going to be 2.89. That would be the initial Y starting point. Good on point 1? All right, now we're going to move on to the second point, which is kind of tricky. It is before the equivalence point, so only some neutralization has occurred. You have both acid and base in the solution, but you have some neutralization. So the first thing we need to do is find the initial concentration. In this case, they're asking for what if you put exactly 20 milliliters in. If they didn't give you a volume to solve for and you were just trying to make a curve, I would pick halfway to the equivalence point. I would figure out the equivalence point was 25 and then do half of that. All right, so if I have 20 milliliters of KOH, and it was actually 20.0, I can then come back to its concentration. And if I multiply the volume by the concentration, the milliliters will cancel out, right? And that will give me then millimoles. I'm going to do 20 times 0.05, which is just 1. I'll go with the 2 sig figs though. And that is millimoles. This is kind of a variation of the molarity equation. If I want to solve for moles, I multiply molarity times liters, but I'm just doing it in the IB units. So this was for the base. Now for the acid, it doesn't ever change throughout this. It's always going to have that 50 milliliters at the 0.025 concentration. And again, I'll use millimoles. Now I want to do 50 times 0.025, which is 1.25. And I'll do sig figs at the end. I just didn't want like the idea of 1 sig fig creeping in here, so I kept that 0.0. So this is my initial concentrations. The next thing I want to do is use the icebox. So when you do, before the equivalence point, you figure out how much has been neutralized by using the volume with the molarity equation. Stoichiometry, basically. These are going to be the concentrations that you put into the icebox. So our initial concentration for the base is 1, and for the acid is 1.25. Let's first talk about this equation though. We have the benzoic acid, and it's reacting with the KOH. So they just left off the K, it's just the OH, but we already talked about how those concentrations are equal, right? So the actual relevant equation doesn't actually include the potassium. We want to figure out how much of the conjugate base there is, and then we've got the water, which we don't need to do anything with in the icebox. So let's go ahead and plug in those initial concentrations that we just got. For the acid, it was 1.25, and for the hydroxide, it was 1. And then the product starts at 0. So now if I am doing the change, it's a 1-to-1 mole ratio, right? So minus X on the left and adding X on the right. So far so good. All right, now here's where it gets a little bit tricky. My KOH completely dissociated into K and OH. So once that runs out, then I'm not going to be pursuing any more of this reaction. That basically makes this the limiting reactant. So the fact that at equilibrium, it will get all used up in this reaction makes that final equilibrium concentration 0, which tells me that X is 1. 1 minus 1 is 0. 1.25 minus 1 is 0.25. And then 0 minus 1, or plus 1, sorry, we're on the product side, so that's just 1. So now I have my equilibrium concentration for my acid and its conjugate base. Now, I can bring in Henderson-Hasselbalch because I have the concentration of the salt, which would be actually a potassium attached to this conjugate base, and the concentration of the acid. So these concentrations are what I'm going to plug in right here. The salt will go here, and the original acid will go here. So we're going to now bring in another equation. Now that we have equilibrium concentrations, we use Henderson-Hasselbalch to get our pH. Since we don't have a hydrogen or hydroxide concentration to deal with. See how we had no hydrogen formed and the hydroxide's gone. So how else would we get the pH? Okay. We're going to need to use Henderson-Hasselbalch now. And one of the first things that we need to be careful of is that we actually use pKa, even though they just gave us Ka. So remember that pKa equals the negative log of the Ka, just like pH equals negative log of H. So the Ka is 6.5 times 10 to the negative fifth. So then that makes the pKa may I help if I can calculate on negative log 6.5 e negative 5, 2 sig figs, so 2 decimal places, 4.19. So that's what I'll plug in here. And then I've got the concentrations from the icebox. So 4.19 plus the log. And now I want to plug in the concentrations. So one small problem, when we calculated these initial concentrations, we actually did it in millimoles, right? So that means these final equilibrium concentrations are of millimoles. So concentration will be these millimoles. The salt was 1, so let's go with 1.0 millimoles. And the base was, acid, I'm sorry, was 0.25 millimoles. So that's supposed to be per milliliter. We originally put in 20 milliliters. So the total volume is that 20 milliliters plus how much acid did we have to start with? The 50 milliliters. So the total volume is actually 70 milliliters. That goes here. The thing is, it really doesn't matter because you can factor that out. You can either calculate it or you can just, like, picture doing a reciprocal of this, that 70 would cancel out. So I'm going to leave it out of the calculation because it really doesn't change it. All right, so now I'm going to do 1 divided by the 0.25. And I want to do the log of that, log of 4. So I got 0.602 and so on. Now I want to add the 4.19. And so I get a final pH of 4.79. So remember, I started at around 2. Now I'm up to about 4.5, 5. pH is increasing as I'm adding more base. Any questions on point 2? All right. So we've got 2 pHs down, 2 to go. Step 3 is actually the most work. At this point, you have equal moles of acid and base. Neither one is limiting. So what we want to do first is find the actual concentrations. The acid concentration is still going to be the same, but now we'll have a new concentration for the base because we've changed the volume. So just for good measure, I guess I can write both. The acid had the 0.025 molarity with the 50 milliliters. Millimoles per milliliter. So we get our answer in millimoles. We did this just a minute ago. 50 times 0.025 is 1.25. And now our new base volume with 25 milliliters instead. And the concentration of the base was doubled. Now I want to do 25 times 0.05, which is also 1.25. Look at that, equal moles of acid and base, or equal millimoles of acid and base. That's kind of our definition of the equivalence. So now we want to write our reaction for the icebox, including both the acid and the base to form the salt and the water, where all of these things are playing a role. So my initial concentrations for both the benzoic acid and the potassium hydroxide are 1.25, where we have 0 of our product, and we don't care about the water. So we're decreasing by X and increasing by X, just like normal. 1 mole of everything. All right, so here's the cool part. Because they have equal moles, they will 100% neutralize each other, meaning there will be none of them left. 0 at the equivalence point, only at the, 0 at equilibrium, only at the equivalence point, which is why I started using EQV, because it's the equilibrium concentrations at the equivalence point that are 0. Yeah. So that gives us X 1.25, right? 1.25 minus X equals 0 in both cases. So then 0 plus 1.25 is 1.25. Keep in mind the units are actually millimoles. All right. Before I move on, I want to get out of this millimole thing and actually have a molarity so that I can use it in the next step. So we want basically millimoles per milliliter, where we have that 1.25 millimoles. Now we got to think about the total volume. If I started with 50 milliliters of the acid, and then I added 25 milliliters of base, my total volume is 75 milliliters. And there was a 0.0 on all the volumes, 3 sixes. Now I want to do, my dot cam does not like my calculator. It pulls it all out of focus, sorry. Come on, focus, focus. Okay. Now I want to do 1.25 divided by 75. So if we keep it to 3 sig figs, it'll be 0.167. Millimoles per milliliter. So this is the actual concentration of the salt. All right, now why did I need that? Let's think about what happens next. So basically, in a solution of equal moles of acid and base, all that's present is the salt in the water, right? So what's going to happen to that salt in water? What happens to the solution of the potassium? I don't know, it's called benzoic acid when it's not acid, and I don't know, whatever this is with the potassium. So that's going to dissociate because all salts 100% dissociate. And so you're going to break this up into potassium and then whatever this conjugate base is. Weak acid, strong conjugate base, organic acid, it came from, right? So we've got this conjugate now in solution, you're going to have hydrolysis. This ion is capable of splitting the water. And so this leads us to a new equilibrium and another icebox in the same question, same part of the question. We're doing a second icebox. Still on step 3. We did the first icebox to figure out how much salt was in solution. Now we got to think about what happens to the salt with the water. And what will happen is it will split the water. We got hydrogen and hydroxide, and then the anion will bond with the cation, and we form this acid, like basically reforming benzoic acid, and then we've got hydroxide kicked out. So we're forming a basic solution. So what we have is the initial concentration of the KC 7H5O2, whatever this same thing, was formed, the salt. And we calculated its concentration, so we can go ahead and use that in the icebox. So 0.167. I'm going to plug in right here. Is there a zero? There was a zero. I'm missing a zero. It was 0.0167. And notice how this is a one-to-one breakdown. So the concentration of the salt is the same as the concentration of this ion. All right, we don't care about our water, and there's zero product. So then we've got our standard change where it's a one-to-one mole ratio, decreasing and increasing. Now we can write this in terms of x, 0.0167 minus x, x, and x. And again, we're just going to go ahead and assume x is small. So now we can write our K expression, but it's not Ka, because we're forming a basic solution. So what we're going to actually write would be Kb. But of course, it's still an equilibrium expression. So it's just Kb equals the products. C6H5COOH and COH over the reactant, leaving out the water, C7H5O2-. That's our Kb expression. Now there's a problem. We don't actually have Kb. What we have is Ka. Now we're going to make another assumption to get us from Ka to Kb. We are going to assume that we are at 25 degrees Celsius. I believe in the notes they have it in Kelvin, 298 Kelvin. We're assuming we're at room temperature. So then we're going to assume Kw is 1 times 10 to the negative 14. So then we know that Ka times Kb equals Kw. We'll plug in Ka, which was 6.5 times 10 to the negative 5th. Solve for Kb, assuming Kw is 1 times 10 to the negative 14. So it'll be 1e negative 14 divided by 6.5 e negative 5. And so I'm going to keep the sig figs the same. So 1.5, and then that's times 10 to the negative 10. Kb. And that is what I need to plug in on the left. Not the Ka, because this wasn't an acid dissociation. This was the basic solution. That'll go in over here, 1.5 times 10 to the negative 10. And then the product concentrations were x, and the reactant concentration is the 0.0167. So on top I have two x's, x squared, and on the bottom I've got the 0.0167. So we can solve for x, which will be 1.5 e negative 10 times 0.0167. And then I need to square root that because it's x squared. And so it would be 1.6 times 10 to the 6, negative 6. Yeah. So it's tempting to go ahead and say, okay, that's equal to hydrogen concentration. But it's not hydrogen, it's hydroxide. If we form hydroxide, X is equal to the hydroxide concentration. Which means we have an extra step in figuring out our pH as well. So if I found the negative log of this concentration, that would actually be the POH. Log 1.6 e negative 6. So here I can find the POH. 2662 decimals is 5 point, actually it's going to be 5.80. So the 5 would round up to 9 and so on. So then we would need to write the 0. So 5.80. And then because again, we are at 25 degrees Celsius, the pH plus the POH add up to 14. So I can find the pH by doing 14 minus 5.80, which would be 8.20. See if that'll flip there. There we go. That's our pH then. Still climbing, even higher than before. We're adding even more base. Notice how that's above 7 as well. We have this basic buffer. And that actually does it for step 3 finally. I'll get on step 3. There's one more step. But point 4 is finally actually a fairly easy step compared to this other stuff. All right. So at this point then, point 4 is after the equivalence point. So now I'm up in the part of the graph where you have excess base. So the assumption here is that the acid is neutralized. And so we just have this base left in the solution. Now the question is just to find out how much is extra. Like, what does excess really mean? So basically, this is the same old Stokes step, but then we're just going to subtract the 2. So for the base, now I have, what was this one for 30 milliliters? Now I have a new volume of 30 milliliters. And the concentration of the base again is 0.05. So the base is 30 times 0.05, 1.5 millimoles. And the acid, which we've done several times now, let's see if I can find one real quick. The acid is still going to be 50 milliliters at a concentration of 0.025. So the acid, we have 1.25 millimoles. The other thing is, once you find the millimoles of the unknown, it's the same. It doesn't change. We're not doing any back titrating anything. So then what's the difference here? 1.5 minus 1.25 would be obviously 0.25, right? Maybe I shouldn't say obviously. Sometimes I don't trust my quick math. Yeah, 0.25. And that is the base having more than the acid. So this is the excess base. You're basically doing the same Stoke to get how much of each is there and then find the difference. So since there's this many millimoles, I can now set up millimoles per milliliter to find my molarity, my concentration, using the 0.25 millimoles. And then the volume now is going to be 30 plus the original 50, so 80 milliliters. Almost done. So 0.25 divided by 80 is 0.00, so 26831. That's our concentration, but of base again, right? So this is basically the molarity of the, like, let's say OH concentration, because it was excess base. So same as last time, when you do negative log of this concentration, you actually get the POH. At 0.0031. That's 2.51. So then the pH is just going to be 14 minus 2.51. That's 11.49. Our highest pH. Big surprise, because now we have all this. So and if we had these 4 pHs, then the next step would be that we could actually have the milliliters of base plotted against the pH, and we could just plot out the 4 pHs, and then you know what the curve's supposed to look like. So you kind of connect the dots from there. This question just specifically asks for the pHs, but the thing you can do with it that's cool is then find the pH. I know that it is now 10:32, so if you guys need to go for it. I'm going to finish the recording though still with going back to the screen share. It'll take me about 3 minutes if you want to stick around to tie indicators back into this. So, webcam, screen share, PowerPoint. So we just did all this math on the paper. All right, so with indicators, indicators are going to tell us when the pH is changing. The idea is that they're going to change when the pH is equal to the pKa. This is known as the endpoint that we did in honors. And the idea is to kind of be that qualitative support. So yes, we are going to use an indicator when we titrate because we want to have some kind of qualitative observation to support it. The thing to know about an indicator is that the color of the acid needs to be a different color than the color of the alkali salt. So the, in this case, they're using IN instead of where we would usually use A for the anion, just to show that's the indicator. So the indicator anion and the indicator acid need to be the things that are a different color. And the reason that the endpoint is so special is because that's when the pH is equal to the pKa. So say, for example, I'm still going to kind of refer to this as A. This is our indicator acid. This would be the A minus we've seen before compared to the weak acid. If those concentrations are equal, and you kind of consider them being factored out here, like 1 divided by 1, they would kind of cancel each other out. Then the K is basically just dependent on the hydrogen ion concentration. So if the K is equal to the hydrogen concentration, then the pK will be equal to the pH. And so that's giving us that the moles of acid are equal to the moles of base. So say, for example, we wanted to pick which indicator we wanted to use based on the pKa values. Here's an example where we have methyl orange with a pK of a low 3.7 and phenolphthalein with a higher pK of 9.6. So one's better for the acid range, one's better for the basic range. So depending on where your equivalence point is, you're going to pick an indicator that changes in that range. So here's an example of a strong acid, strong base. Maybe the methyl would be a better indicator. But if you had some buffering action where it was weak, maybe the phenolphthalein would be a better indicator. So you really have to know your equivalence point first and then pick out an indicator that changes in that range. All right. I'm going to go ahead and stop the recording now.